Hello, welcome back. It's Thursday. It will be a long, hot day, one of the hottest days in the whole year. But it's not supposed to be hot now because it's autumn. So that will be like 30 degrees outside. So it's in 2 days is September. It's not supposed to be so hot because we end up the long summer is the 29th. I'm getting my pension tomorrow and I have to wait the whole weekend to 2nd September to pay my rent apartment. Then I have a big payment to a shopping credit, no, a credit card debt, $350 Wednesday. And I have $300 left for food. And I was shopping this Chinese Temu. I did buy a new tent bag to my tent bag project. So, but I don't like to think about all that now. So it's 11 a.m. So just like to read some space my whole day. Just to go through my long day, this long hot day. I think I have to label my camcorder a little bit. So let's do, oh, I have to close my door. It's supposed to be 30 degrees end of August in Denmark. Because it's not the summer anymore. It's autumn.
Rocket engine. A rocket engine uses stored rocket propellants as the reaction mass for forming a high-speed propulsive jet of fluid, usually high-temperature gas. Rocket engines are reaction engines, producing thrust by ejecting mass rearward, in accordance with Newton's third law. Most rocket engines use the combustion of reactive chemicals to supply the necessary energy, but non-combusting forms such as cold gas thrusters and nuclear thermal rockets also exist. Vehicles propelled by rocket engines are commonly used by ballistic missiles. They normally use solid fuel and rockets. Rocket vehicles carry their own oxidizer, unlike most combustion engines, so rocket engines can be used in a vacuum to propel spacecraft and ballistic missiles. Compared to other types of jet engine, rocket engines are the lightest and have the highest thrust, but are the least propellant efficient. They have the lowest specific impulse. The ideal exhaust is hydrogen, the lightest of all elements, but chemical rockets produce a mix of heavier species, reducing the exhaust velocity. Rocket engines become more efficient at high speeds, due to the Oberth effect. Terminology, edit. Here, rocket is used as an abbreviation for rocket engine. Thermal rockets use an inert propellant, heated by electricity, electrothermal propulsion, or a nuclear reactor, nuclear thermal rocket. Chemical rockets are powered by exothermic reduction-oxidation chemical reactions of the propellant. Solid fuel rockets, or solid propellant rockets or motors, are chemical rockets which use propellant in a solid state. 2 liquid propellant rockets use one or more propellants in a liquid state fed from tanks. 3 hybrid rockets use a solid propellant in the combustion chamber, to which a second liquid or gas oxidizer or propellant is added to permit combustion. 4 monopropellant rockets use a single propellant decomposed by a catalyst. The most common monopropellants are hydrazine and hydrogen peroxide. Principle of operation, edit. Rocket engines produce thrust by the expulsion of an exhaust fluid that has been accelerated to high speed through a propelling nozzle. The fluid is usually a gas created by high pressure, 150 to 4,350 pound per square inch, 10 to 300 bar, combustion of solid or liquid propellants, consisting of fuel and oxidizer components, within a combustion chamber. As the gases expand through the nozzle, they are accelerated to very high, supersonic, speed, and the reaction to this pushes the engine in the opposite direction. Combustion is most frequently used for practical rockets, as the laws of thermodynamics, specifically Carnot's theorem, dictate that high temperatures and pressures are desirable for the best thermal efficiency. Nuclear thermal rockets are capable of higher efficiencies, but currently have environmental problems which preclude their routine use in the Earth's atmosphere and cislunar space. For model rocketry, an available alternative to combustion is the water rocket pressurized by compressed air, carbon dioxide, nitrogen, or any other readily available, inert gas. Propellant, edit. Rocket propellant is mass that is stored, usually in some form of tank, or within the combustion chamber itself, prior to being ejected from a rocket engine in the form of a fluid jet to produce thrust. Chemical rocket propellants are the most commonly used. These undergo exothermic chemical reactions producing a hot gas jet for propulsion. Alternatively, a chemically inert reaction mass can be heated by a high-energy power source through a heat exchanger in lieu of a combustion chamber. Solid rocket propellants are prepared in a mixture of fuel and oxidizing components called grain, and the propellant storage casing effectively becomes the combustion chamber. Injection, edit. Liquid-fueled rockets force separate fuel and oxidizer components into the combustion chamber, where they mix and burn. Hybrid rocket engines use a combination of solid and liquid or gaseous propellants. Both liquid and hybrid rockets use injectors to introduce the propellant into the chamber. These are often an array of simple jets holes through which the propellant escapes under pressure, but sometimes may be more complex spray nozzles. When two or more propellants are injected, the jets usually deliberately cause the propellants to collide as this breaks up the flow into smaller droplets that burn more easily. Combustion chamber, edit. For chemical rockets, the combustion chamber is typically cylindrical, and flame holders, used to hold a part of the combustion in a slower flowing portion of the combustion chamber, are not needed. The dimensions of the cylinder are such that the propellant is able to combust thoroughly. Different rocket propellants require different combustion chamber sizes for this to occur. This leads to a number called L raised to the asterisk power. The characteristic length L raised to the asterisk power equals the fraction with numerator V sub c and denominator A sub t, where 1 V sub c is the volume of the chamber, 2 A sub t is the area of the throat of the nozzle. L asterisk is typically in the range of 64,152 centimeters, 2560 in. The temperatures and pressures typically reached in a rocket combustion chamber in order to achieve practical thermal efficiency are extreme compared to a non-afterburning air-breathing jet engine. No atmospheric nitrogen is present to dilute and cool the combustion, so the propellant mixture can reach true stoichiometric ratios. This, in combination with the high pressures, means that the rate of heat conduction through the walls is very high. In order for fuel and oxidizer to flow into the chamber, the pressure of the propellants entering the combustion chamber must exceed the pressure inside the combustion chamber itself. This may be accomplished by a variety of design approaches including turbo pumps or, in simpler engines, via sufficient tank pressure to advance fluid flow. Tank pressure may be maintained by several means, including a high-pressure helium pressurization system common to many large rocket engines or, in some newer rocket systems, by a bleed-off of high-pressure gas from the engine cycle to autogenously pressurize the propellant tanks. For example, the self-pressurization gas system of the SpaceX Starship is a critical part of SpaceX's strategy to reduce launch vehicle fluids from 5 in their legacy Falcon 9 vehicle family to just 2 in Starship, eliminating not only the helium tank pressurant but all hypergolic propellants as well as nitrogen for cold gas reaction control thrusters. Nozzle, edit. Main article, rocket engine nozzle. The hot gas produced in the combustion chamber is permitted to escape through an opening, the throat, and then through a diverging expansion section. When sufficient pressure is provided to the nozzle, about 2.53 times ambient pressure, the nozzle chokes and a supersonic jet is formed, dramatically accelerating the gas, converting most of the thermal energy into kinetic energy. Exhaust speeds vary, depending on the expansion ratio the nozzle is designed for, but exhaust speeds as high as 10 times the speed of sound in air at sea level are not uncommon. About half of the rocket engine's thrust comes from the unbalanced pressures inside the combustion chamber, and the rest comes from the pressures acting against the inside of the nozzle. See diagram. As the gas expands, adiabatically, the pressure against the nozzle's walls forces the rocket engine in one direction while accelerating the gas in the other. The most commonly used nozzle is the de Laval nozzle, a fixed geometry nozzle with a high expansion ratio. The large bell or cone-shaped nozzle extension beyond the throat gives the rocket engine its characteristic shape. The exit static pressure of the exhaust jet depends on the chamber pressure and the ratio of exit to throat area of the nozzle. As exit pressure varies from the ambient, atmospheric pressure, a choked nozzle is said to be 1. Under-expanded, exit pressure greater than ambient. 2. Perfectly expanded, exit pressure equals ambient. 3. Over-expanded, exit pressure less than ambient, shock diamonds form outside the nozzle, or 4. Grossly over-expanded, a shock wave forms inside the nozzle extension. In practice, perfect expansion is only achievable with a variable exit area nozzle, since ambient pressure decreases as altitude increases, and is not possible above a certain altitude as ambient pressure approaches zero. If the nozzle is not perfectly expanded, then loss of efficiency occurs. Grossly over-expanded nozzles lose less efficiency, but can cause mechanical problems with the nozzle. Fixed area nozzles become progressively more under-expanded as they gain altitude. Almost all de Laval nozzles will be momentarily grossly over-expanded during startup in an atmosphere. Nozzle efficiency is affected by operation in the atmosphere because atmospheric pressure changes with altitude, but due to the supersonic speeds of the gas exiting from a rocket engine, the pressure of the jet may be either below or above ambient, and equilibrium between the two is not reached at all altitudes. See diagram. Back pressure and optimal expansion, edit. For optimal performance, the pressure of the gas at the end of the nozzle should just equal the ambient pressure. If the exhaust's pressure is lower than the ambient pressure, then the vehicle will be slowed by the difference in pressure between the top of the engine and the exit. On the other hand, if the exhaust's pressure is higher, then exhaust pressure that could have been converted into thrust is not converted, and energy is wasted. To maintain this ideal of equality between the exhaust's exit pressure and the ambient pressure, the diameter of the nozzle would need to increase with altitude, giving the pressure a longer nozzle to act on, and reducing the exit pressure and temperature. This increase is difficult to arrange in a lightweight fashion, although is routinely done with other forms of jet engines. In Rocketry, a lightweight compromise nozzle is generally used, and some reduction in atmospheric performance occurs when used at other than the design altitude or when throttled. To improve on this, various exotic nozzle designs such as the plug nozzle, stepped nozzles, the expanding nozzle and the aerospike have been proposed, each providing some way to adapt to changing ambient air pressure and each allowing the gas to expand further against the nozzle, giving extra thrust at higher altitudes. When exhausting into a sufficiently low ambient pressure, vacuum, several issues arise. One is the sheer weight of the nozzle. Beyond a certain point, for a particular vehicle, the extra weight of the nozzle outweighs any performance gained. Secondly, as the exhaust gases adiabatically expand within the nozzle, they cool, and eventually some of the chemicals can freeze, producing snow within the jet. This causes instabilities in the jet and must be avoided. On a de-level nozzle, exhaust gas flow detachment will occur in a grossly over-expanded nozzle. As the detachment point will not be uniform around the axis of the engine, a side force may be imparted to the engine. This side force may change over time and result in control problems with the launch vehicle. Advanced altitude compensating designs, such as the aerospike or plug nozzle, attempt to minimize performance losses by adjusting to varying expansion ratio caused by changing altitude. Propellant efficiency, edit. See also, specific impulse. For a rocket engine to be propellant efficient, it is important that the maximum pressures possible be created on the walls of the chamber and nozzle by a specific amount of propellant, as this is the source of the thrust. This can be achieved by all of 1. Heating the propellant to as high a temperature as possible, using a high-energy fuel, containing hydrogen and carbon and sometimes metals such as aluminium, or even using nuclear energy. 2. Using a low specific density gas, as hydrogen-rich as possible. 3. Using propellants which are, or decomposed to, simple molecules with few degrees of freedom to maximize translational velocity. Since all of these things minimize the mass of the propellant used, and since pressure is proportional to the mass of propellant present to be accelerated as it pushes on the engine, and since from Newton's third law the pressure that acts on the engine also reciprocally acts on the propellant, it turns out that for any given engine, the speed that the propellant leaves the chamber is unaffected by the chamber pressure, although the thrust is proportional. However, speed is significantly affected by all three of the above factors, and the exhaust speed is an excellent measure of the engine propellant efficiency. This is termed exhaust velocity, and after allowance is made for factors that can reduce it, the effective exhaust velocity is one of the most important parameters of a rocket engine, although weight, cost, ease of manufacture etc. are usually also very important. For aerodynamic reasons the flow goes sonic, chokes, at the narrowest part of the nozzle, the throat. Since the speed of sound in gases increases with the square root of temperature, the use of hot exhaust gas greatly improves performance. By comparison, at room temperature the speed of sound in air is about 340 m/s, while the speed of sound in the hot gas of a rocket engine can be over 1700 m/s. Much of this performance is due to the higher temperature, but additionally rocket propellants are chosen to be of low molecular mass, and this also gives a higher velocity compared to air. Expansion in the rocket nozzle then further multiplies the speed, typically between 1.5 and 2 times, giving a highly collimated hypersonic exhaust jet. The speed increase of a rocket nozzle is mostly determined by its area expansion ratio, the ratio of the area of the exit to the area of the throat, but detailed properties of the gas are also important. Larger ratio nozzles are more massive but are able to extract more heat from the combustion gases, increasing the exhaust velocity. Thrust vectoring, edit. Main article, thrust vectoring. Vehicles typically require the overall thrust to change direction over the length of the burn. A number of different ways to achieve this have been flown. 1. The entire engine is mounted on a hinge or gimbal and any propellant feeds reach the engine via low-pressure flexible pipes or rotary couplings. 2. Just the combustion chamber and nozzle is gimballed, the pumps are fixed, and high-pressure feeds attached to the engine. 3. Multiple engines, often canted at slight angles, are deployed but throttled to give the overall vector that is required, giving only a very small penalty. 4. High-temperature vanes protrude into the exhaust and can be tilted to deflect the jet. Overall performance, edit. Rocket technology can combine very high thrust, meganewtons, very high exhaust speeds, around 10 times the speed of sound in air at sea level, and very high thrust forward/weight ratios, 100, simultaneously, as well as being able to operate outside the atmosphere, and while permitting the use of low pressure and hence lightweight tanks and structure. Rockets can be further optimized to even more extreme performance along one or more of these axes at the expense of the others. Specific impulse, edit. Main article, specific impulse. The most important metric for the efficiency of a rocket engine is impulse per unit of propellant. This is called specific impulse, usually written I sub SP. This is either measured as a speed, the effective exhaust velocity, V sub E, in meters forward/second or feet forward/s, or as a time, seconds. For example, if an engine producing 100 pounds of thrust runs for 320 seconds and burns 100 pounds of propellant, then the specific impulse is 320 seconds. The higher the specific impulse, the less propellant is required to provide the desired impulse. The specific impulse that can be achieved is primarily a function of the propellant mix, and ultimately would limit the specific impulse, but practical limits on chamber pressures and the nozzle expansion ratios reduce the performance that can be achieved. Net thrust, edit. Main article, thrust. Below is an approximate equation for calculating the net thrust of a rocket engine. F sub n equals m dot above v sub e equals m dot above v sub e minus opt plus a sub e times open paren p sub e minus p sub a m b close paren, where m dot above equals exhaust gas mass flow, v sub e equals effective exhaust velocity, sometimes otherwise denoted as C in publications, v sub e minus opt equals effective jet velocity when PAM equals P. A sub E equals flow area at nozzle exit plane, or the plane where the jet leaves the nozzle if separated flow. P sub E equals static pressure at nozzle exit plane. P sub AMB equals ambient, or atmospheric, pressure. Since, unlike a jet engine, a conventional rocket motor lacks an air intake, there is no ram drag to deduct from the gross thrust. Consequently, the net thrust of the rocket motor is equal to the gross thrust, apart from static back pressure. The m dot above v sub e minus opt term represents the momentum thrust, which remains constant at a given throttle setting, whereas the a sub e times open paren p sub e minus p sub a m b close paren term represents the pressure thrust term. At full throttle, the net thrust of the rocket motor improves slightly with increasing altitude, because as atmospheric pressure decreases with altitude, the pressure thrust term increases. At the surface of the Earth, the pressure thrust may be reduced by up to 30%, depending on the engine design. This reduction drops roughly exponentially to zero with increasing altitude. Maximum efficiency for a rocket engine is achieved by maximizing the momentum contribution of the equation without incurring penalties from over-expanding the exhaust. This occurs when P sub E equals P sub A mb. Since ambient pressure changes with altitude, most rocket engines spend very little time operating at peak efficiency. Since specific impulse is force divided by the rate of mass flow, this equation means that the specific impulse varies with altitude. Vacuum-specific impulse, ISP, edit. Due to the specific impulse varying with pressure, a quantity that is easy to compare and calculate with is useful. Because rockets choke at the throat, and because the supersonic exhaust prevents external pressure influences traveling upstream, it turns out that the pressure at the exit is ideally exactly proportional to the propellant flow. Above. Provided the mixture ratios and combustion efficiencies are maintained. It is thus quite usual to rearrange the above equation slightly. F sub VAC equals C sub F times m dot above C raised to the asterisk power. And so define the vacuum ISP to be V sub E VAC equals C sub F times C raised to the asterisk power, where C raised to the asterisk power equals the characteristic velocity of the combustion chamber, dependent on propellants and combustion efficiency. C sub F equals the thrust coefficient constant of the nozzle, dependent on nozzle geometry, typically about 2. And hence, F sub n equals m dot above V sub E VAC minus A sub E times P sub A mb. Throttling, edit. Rockets can be throttled by controlling the propellant combustion rate. M dot above. Usually measured in kg/s or pound/s. In liquid and hybrid rockets, the propellant flow entering the chamber is controlled using valves. In solid rockets it is controlled by changing the area of propellant that is burning, and this can be designed into the propellant grain, and hence cannot be controlled in real time. Rockets can usually be throttled down to an exit pressure of about 1/3 of ambient pressure, often limited by flow separation in nozzles, and up to a maximum limit determined only by the mechanical strength of the engine. In practice, the degree to which rockets can be throttled varies greatly, but most rockets can be throttled by a factor of 2 without great difficulty. The typical limitation is combustion stability, as for example, injectors need a minimum pressure to avoid triggering damaging oscillations, chugging or combustion instabilities, but injectors can be optimized and tested for wider ranges. For example, some more recent liquid propellant engine designs that have been optimized for greater throttling capability, B3, Raptor, can be throttled to as low as 18–20% of rated thrust. Solid rockets can be throttled by using shaped grains that will vary their surface area over the course of the burn. Energy efficiency, edit. Further information, rocket energy efficiency. Rocket engine nozzles are surprisingly efficient heat engines for generating a high-speed jet, as a consequence of the high combustion temperature and high compression ratio. Rocket nozzles give an excellent approximation to adiabatic expansion, which is a reversible process, and hence they give efficiencies which are very close to that of the Carnot cycle. Given the temperatures reached, over 60% efficiency can be achieved with chemical rockets. For a vehicle employing a rocket engine, the energetic efficiency is very good if the vehicle speed approaches or somewhat exceeds the exhaust velocity, relative to launch, but at low speeds the energy efficiency goes to 0% at zero speed, as with all jet propulsion. See rocket energy efficiency for more details. Thrust-to-weight ratio, edit. Main article, thrust-to-weight ratio. Rockets, of all the jet engines, indeed of essentially all engines, have the highest thrust-to-weight ratio. This is especially true for liquid-fueled rocket engines. This high performance is due to the small volume of pressure vessels that make up the engine, the pumps, pipes and combustion chambers involved. The lack of inlet duct and the use of dense liquid propellant allows the pressurization system to be small and lightweight, whereas duct engines have to deal with air which has around 3 orders of magnitude